Hello, good evening, and welcome to the webinar for the new CivilFEM 2016, CivilFEM powered by Mark. This is a presentation about the new features, and for those of you who don't know them, the software is a little presentation about it. Here with me is my colleague Ronald Siat.
Hello, I'm Ronald Siat. Thank you all for attending, wherever you are, okay?
Okay, so we can start. Okay, CivilFEM is a powered by Mark. It's a unique solution targeted to the civil engineer market. It's a very powerful tool, and it can perform analysis from the most simple ones to the most advanced, like construction simulation, constructed process simulation, being non-linear. So we like to say that it's only one software for all your civil engineer needs. It's all developed in-house by Ingeciber. Ingeciber is full responsible for the development and distribution. You see, it needs CivilFEM support distributor network. So everything is done in-house here in Madrid. Okay. The main characteristics of CivilFEM is a very customizable software. We can import and export geometry, and we have the ability to enter data using parametric formulas and scripts and macros with Python. We want to stress this feature because it's a very powerful capability we have. Everything you see in the graphical user interface can be performed by a macro script of Python. The software is object-oriented in its architecture. This means that everything inside CivilFEM is an entity, is an object that can be modified and using the property pane and grouped together in a conceptual manner using groups like we are going to see a little after. Okay, we have several advanced features that any modern software should have, like 64-bit support, parallel processing, and a very flexible floating license system. And we can generate automatic analysis report for the current model. We include all the typical analysis types of any final element software and many more, like linear and nonlinear static analysis, transient, backlink, and modal and spectrum analysis, harmonic analysis too, and we include several advanced features that many products don't offer, like creep and syncage of concrete, and several models for advanced material behavior. Very nice evolutive construction process system where you can take into consideration the different ages of the materials. We have cracking and crack propagation modeling, heat transfer, and seepage analysis. So these are all the type of analysis CivilFEM can perform in a nutshell. Okay. CivilFEM is for solving the model. CivilFEM uses the MSC software solver called Mark. MSC software is the company responsible for the development and distribution of Patra and Nastran, for example, or Apex. So MSC Mark is a very powerful nonlinear software. This gives us the ability to perform all the advanced models and analysis we have talked before. And with that, we use the CivilFEM easy-to-use graphical interface that is tailored for civil engineers. So it's a very well integrated package. You use the CivilFEM graphical user interface, and then internally we use the MSC software Mark solver for solving the nonlinear case or the modeling of the model you have entered. Okay, about the graphical user interface, It's a typical modern user interface of you can see in, for example, in Microsoft Office or similar software. It is multi-language. We have floating and dockable windows. You can move them and rearrange them as you please. As we said before, we have everything can perform using menus or commands using Python. So this makes the software totally customizable, and everything can be changed inside the software. We like to talk about the flexible unit system we have. This is a unique feature. You can mix and match every unit you want, and internally CivilFEM will transform those units into the chosen ones. So you don't need to keep doing hand calculations of the unit system.
Yeah, after this short presentation, we will open a demo with the software, so we can see some of these features with the practicing with the software. Okay.
Okay, for this new 2016 version, we have included several new features like a new and faster graphical interface. This allows a very fast modeling process, and the visualization has been greatly improved. We have a new heads-up display that allows us to switch between 3D models. So now we have a geometry view and a structural element view selectable from the heads-up display. We have several new selection filters for structural elements. Now you can select entities by a structural element or a finite element or nodes. And we have included the option to pick and get the coordinates from points or nodes directly into the 3D view. Okay, we have improved the grid. This grid now has a better usability and several new options, so you can it will be much more useful than before. Now you can zoom to fit the model using the selected entities, using groups. We have improved the box selection option. Now you can drag the box selection from top to bottom or bottom to top, and the behavior will be different, just like in many CAD systems like AutoCAD, for example. The camera can be oriented quickly using the three axes on the bottom left of the view pane. And we have improved the visualization of loads and boundary conditions and mass visualization. Okay, about the geometry tools, we have all the tools we already have for performing the geometry of the model, from lines to surfaces to volumes. Those can be easily used in CivilFEM to create any complex geometry. We have new Boolean operations and improved geometry translation operations. And of course, any CAD model from AutoCAD or any other software can be imported into CivilFEM and modified inside it. We have included a new multi-copy operation option, so you can create multiple copies of elements, and you can choose if they are independent from the original one. And we have included a new model option, model group selection and selection groups options. Now, this is an animated example of these new features. We have a new model group option where you can group your model using this tool, and we can create selection groups where you can define a selection group by picking or by adding
by material,
materials.
by cross section.
Okay. About the materials, CivilFEM always has have a very extensive material library. We have several structural engineering materials like steel, concrete, reinforced steel, or prestressed steel, apart from the soil materials and rocks, we have a linear and nonlinear behavior of every material. So you can perform advanced analysis or time-dependent analysis depending on the age of concrete, for example, like is shown in the picture down here. We have reorganized and improved the soil material library, so it's now more clear and useful. And we have included a very advanced modified can-clay plasticity model, where you can perform a can-clay model on soils using the yield conditions, constitutive law, hardening law, and flow rule. That's the way you can define the advanced can-clay model and perform a soil analysis of your foundation.
Yes. Well, the next step will be to define cross sections. If it's the case, if we are using beam elements, we can define any cross section for steel and concrete. Okay, we can define them using our library, a complete library for hot roll shapes for the steel case, or setting the typical dimensions for concrete or for steel. But if we want to generate other shape or other section which is not in the library, we can use the steel by plates option. So here you can see we can define for beams this. We have an utility to define the different plates, and then later use this section to mesh or line and define our in this case this bridge element. Okay, bridge model with beam elements. For the case of concrete, we can define a 2D mesh of our section. We can use set rebars, okay, reinforcement steel, reinforcing steel inside using bars or using a mount by separation, using different diameters of bars, and then use this section to mesh our line. Okay, all these figures show beam elements. Okay. Well, all the proper section mechanical properties of the section will be automatically defined and calculated. Okay. The next process is the mesh. The mesh capabilities are in CivilFEM were improved. Okay, we have tools to mesh beam, shell, and solid elements. The meshing process has been optimized. One of the new enhancements is the ability to reverse the mesh element orientation. If we need to do that if the results are not they not please us, we can reverse, for example, the set direction of our axis, in the case for reinforcement amount results, or for contact analysis. Sometimes we have to reverse the direction of some axis of the elements which will be in contact. Okay. Well, as you see, CivilFEM we can work using the graphical user interface, but Python programming is always useful for any repeated operation. Okay, Python can be used anytime. Other new capability is the cable modeling. Okay, we have new structural element, which is the cable, which will have only a tension behavior. Okay, continue with the mesh tab. We have, as you see here, we have new model utils, which are the nonlinear rotational springs. We have nodes connection entities. Here you can see in this animation how to define a new connection. One node will be the master node, which will be tied to, all the tied nodes will be coupled to the master node, so we can set any kind of couplings, or we can release any kind of degree of freedom, displacements or rotations. They can be set rigid by default, but we can set coefficients or stiffness if we want to set a spring. Okay, so we can change the behavior between connection between the typical fixed connection where all the degrees of freedom are coupled. We can uncouple them with this utility. Okay, for contacts as well, we implemented a new algorithm coming from our solver, which is the segment to segment. As well, we have masses and insertion tool, which they were defined in the previous versions. But for contacts, with this new segment to segment algorithm, the contact process is easier, and we will not. It won't depend on not as much as before on the mesh. Okay, we just define which will be the two entities in contact for the glue case or touching case, and just set some nonlinear configuration option for convergence, and that's it. Okay, later we will see some example for this. Well, the typical loading tools. After meshing, we can define any point loads, point single moments, linear surface loads, and then temperatures, as well for the static case or pseudo-static case. We can add a spectrum. For the dynamic case, we can add tables of acceleration versus time, or we can set an harmonic load when frequency has to be taken into account. Okay, and the same for boundary conditions. Boundary conditions, you can set any type of constraint. Okay, it can be even springs if you want to set a flexible soil, or set a elastic foundation stiffness. Okay, we have a complete range of tools to define our model. Okay, and if we want to set advanced loadings, we have always the help of the Python programming. Okay. For solution and results are new enhancements, and we can highlight the compression option of the results file. Now it can be reduced up to 50%, our results file. Okay, you can choose that in the solution tab. For non-linear analysis, we have now the convergence monitor. Okay, will be very useful to know if our model will have a convergence at the end or not. Monitoring the residual and displacement residual results. And we have another capability, which if we want to obtain results from a previous analysis, we can get some initial previous state, which can be previous stresses or displacements, which were calculated in a previous analysis while using the same mesh, of course. Okay, in these videos, you can see some animations of the typical results that can be done in CivilFEM. One is on the left is a moving load, and the other are two beams in contact. Okay, all the results that are shown here can be using for the beam case or shell size, using the enhanced results, which are showing the real size or shape of the model. Or sometimes it's we can be more useful to show a 2D view. Okay, other charts that are available are the ones, for in this case we have this figure showing the displacement with damping a long time and a transient analysis. So we have a lot of tools to plot results. Well, as well, we have once we have our results file, we can using the derived results, change any sign or multiplying some certain results by a coefficient. So in this case, it will be very useful to define a seismic combination where we want to change the sign of some results of the forces and moments, because we want to set a combination later. As usually the combination of modes of a seismic analysis will usually come in absolute value. As you see here, the user combination tool, we can select the different results and then combine them using the factors or safety factors or coefficients which are specified in the code or standard. Another tools are forces in springs and mass, is shown now after solving. As Javier told you before, as we can set groups or components, now we can plot them. We can plot results, or we can check those groups which were selected previously. And always list and use Python as always. Okay. The new codes are the ones highlighted. The American code for concrete, the ACI code, the 318 and 349 for the nuclear facilities, for nuclear concrete parts, and as well we developed the last version of AISC structural steel of American code. Okay, and along with that we still have all the other codes which are shown here. The Indian standard for the last version of the Indian standard, as well for steel structures, is developed, is implemented.
Okay, so we are now going to open the software so you can see 3 examples we have made for you for this presentation.
Okay, this is our window.
Okay.
Our main window.
Okay, we're going to create a new case, a new static case first. So first of all, I'm going to open the property pane. Okay. Okay, so we want to start talking about the logical steps to perform analysis in CivilFEM. CivilFEM is designed to be used from left to right and top to bottom, so we have the several tabs in order of where we want to perform the analysis. So we start here in environment. Here you can choose your code or your structural or steel code or reinforced concrete code, and the unit system you want to use, and the configuration, the general configuration for the model. So we are going to leave it as it is, so we can by default. Okay. So first of all, we want to show the new heads-up display. This allows us to select several entities depending on their kind. So we can select points, lines, surfaces, and volumes. And this is then the grid option. So we can show the grid here and rotate it to center the view on the grid. Of course, we can select the configuration for the grid if we want to change something. Okay, we are going to zoom in and we are going to create a line. This is an example of a cooling tower, a simplified cooling tower. We are going to perform a spectral model, a spectral analysis. So first we need to create the line for the generation of the surface. So we start out at the origin and we can finish our line here. Now CivilFEM has a zoom in to zoom the line, and now we need to create the arc for the surface. So we go to geometry, we create the arc. So for example, we can choose this point, and this one. Okay, Here you can see that the hazard display is changing depending on what you have to click. You can go back to the previous selection, clicking this arrow. And this will navigate through the property pane, and you can select any other mid vertex or start vertex, just clicking on the navigation arrow here. So we click OK. We like what we created, and now we have the line we want to generate the surface with. So now we are going to create the revolution. Okay, we choose the axis, and then we choose the line, the geometric entity, and we click OK. So this is our simplified cooling tower. Now the next step is creating the materials. We want to create a concrete material for the shell and a reinforcement material for the design of the reinforcement of the cooling tower. So we first create a material. For example, we're going to use the Spanish material library, and we are going to select this one. Here we like to talk about the features, the advanced features of material we have. For concrete, you can select the linear behavior or shorten loss diagram. That is includes several nonlinear models like Bourque-Courtois. I'm going to show you now here. Multilinear elastic or nonlinear isotropic hardening. This will perform a nonlinear analysis of concrete. And of course, we have cracking options, and we have the code properties, and design a stress strain diagram showing the different values for concrete depending on the day it is created. As you know, concrete hardens during time, so if you want to perform an evolutive analysis, you can use the concrete on before hardening. So here's are the curves that we are going to use in case that this kind of analysis will be performed.
Yeah, if we want to see the cracking options, if for the assist in predicting crackinization and in simulating tension, softening, plastic yielding, and crushing. Okay, in case we want to perform this kind of analysis, we have this data to be set.
Okay.
Okay, in this case, our analysis will be just linear.
I'm going to leave the linear behavior here. So then we can choose our reinforcement steel. I'm going to choose another typical steel for reinforcement. Okay. And now all our materials are created. Here you can see them on the right. And now the next step, we went from model. We don't need to create any cross section because this is a shell. So we're going to go directly to the mesh menu and create our shell. Our shell, we're going to choose the concrete material and the thickness. We want to create. We want to show you another feature. Is the parameters pane. So we are going to show it. Here we have the parameter list. Okay, here. Okay. Here we have the parameter list. So instead of entering the thickness value, we want to create a new parameter. So we're going to call it th, and this is a length parameter. We're going to use meters, and we're going to use a formula, for example, 35 divided by 100. Okay, so the value for the shell is 0.35. So instead of entering here, we can choose instead to enter the name of the parameter, and CivilFEM will automatically convert the parameter to its value. If you want to change the value, you can change the value here in the formula, and CivilFEM will update the property pane accordingly. So here we have 0.3 meters, and this way you can interact with the parameters using parameters inside parameters. So it's a very flexible way to define a model. Okay, so now we click OK, and we have our mesh element created, and we can now choose our mesh controls for actual mesh we want to create. We are going to say we want to control the number of divisions, and we are going to divide the model in 30 in the U direction and 30 in the V direction. So this will create a finer mesh for us. And now after this we can mesh the model. The reinforcement will be defined later because we are going to define the design at the later step. Okay, we are going to create the we are going to save the model before meshing. Okay, now CivilFEM is going to start meshing, and we have the model is already meshed. So as you can see, the heads-up display has changed. Now we have two options. We have the geometry option, the geometry view, and the structural element view. So we can change between them as quickly as that. So the next step from mesh is loads. We want to create one load for our spectral analysis. We're going to use the Eurocode 8 spectrum, and we're going to introduce the 2 meter divided by second square. For acceleration, you can change the type of soil or spectrum, just as defined on the Eurocode 8. We click OK, and now we need to select the damping for the spectrum. Instead of defining the damping on the actual material, we are going to define it here on the spectrum itself. Okay, I need to change, as the vertical axis is Y, we need to change the vertical axis here accordingly. This is 1 and this is 0. We want to change the number of nodes too, because 20 is a bit too much, so we are going to say 10, and the modal combination method, we are going to use the square root system. Okay, we can see the spectrum introduced by points that appears on the Eurocode. So this is the actual spectrum we are going to apply to the model. Of course, it can be modified, but we are going to leave it there as by default. So this is our spectrum. The next thing we need to create is a boundary condition group. We are going to click OK. And now, instead of creating the boundary conditions using a line, we are going to use one of the new features of CivilFEM. That's the direct node selection. So here we can select the whole structural element or several sub-elements of the mesh, or we can use the node selection. Of course, we can change the view, rotate the view, and we can clicking on the axis, we can go back to the previous view. This is another new feature that eases the visualization of the model. So now we are going to select the nodes, the lower nodes of the model. Now all the lower nodes of the model are created, and as you can see here, we have several conditions for the loads of boundary conditions of the model of that selected nodes. We have a nodal constraint that we want to use. So we are going to click on all constraints, and as you can see here, we have all the selected nodes where we are going to apply the constraints. Okay, so we click OK, and now here we have the boundary condition group, and we can see the nodes, and we can show them here. They are where the nodes were selected. Okay, last we have to create the load case. So we have to add the spectrum load, and we are going to apply a factor like well, it's very usual for code checking for applying a factor. So
in this case, we are going to apply only just one structural load.
And we have to add the boundary condition, of course, so that That's our case, the boundary condition plus the spectrum. We are going to perform now the analysis. We need to select now in solve a couple of options for configuration. As we want to create a spectrum model analysis, we have to create the model results. So we click here, and I think that's it. So we can launch the analysis. Okay, the model has been solved, and we have obtained the results. I'm going to click here. Okay, so we can see the output too. Okay, now as the model is solved, we can load the results. First, we are going to load the model results. These are the 10 modes we have extracted, so we can see them here. And we can show, for example, the X component of displacement, and plot the deformed shape and see what the modes look like. This is the second mode, the third mode, fourth, and so on. So of course we can show information, not only just the graphic, but we can show the actual values of the
frequency, periods, participation factors for each degree of freedom, mobilized masses, okay,
etc. So now that we have the modes, we can see the results for the actual spectrum.
When all the modes are combined according to the square root of the sum of the squares.
Okay, so here is I'm going to change the units to centimeters, and here are the displacement. As you can see, the displacements are very low because it's the only load applied. If we had a wind load, for example, the displacement will be much bigger, but you get the idea of the model. Here you can see the deformed shape of this spectrum. And now one interesting thing we can do is performing a design of cells. I'm going to turn off the grid first, and we can design the cells using the reinforced material we defined before. I'm going to use the wood armor, for example, for cells, and just like that, the design of the cell is performed.
Yeah, with this utility, we will obtain the reinforcement according to this design method that needs this structure according to the loads applied.
Okay, so now we can show, for example, the reinforcement about at the Y bottom.
And we can choose any kind of units that you have, regardless the model units. We can choose even the Imperial British units, mixing even if they are not consistent. Okay, we have this all this kind.
And this is the design process of a cooling tower. So now we're going to open another model for you.
Yes. Well, we just finished this consultant project, okay, which is, well, the client or customer wanted to analyze this steel joint, okay. We have we define different groups, okay, as these are new utility, okay. These are the bolts. This is one shell which is connected to another. This T plate is connected to this another plate, okay, which is simple in contact. And the client, actually this structure supports a curtain wall on this side, and on the other side is linked to the slab of our concrete floor. Okay, so the analysis just is to know just to check if the steel will reach the yield limit state, and check as well displacements, or if this or how will be the behavior of this plate when the forces are applied. The forces are applied using tie-ins. Okay, the bolts were simulated as you see here. The bolts were simulated using tying connections. We can see here these tie-ins where one load will the loads will be, we'll see here, the loads will be applied on the master node, and this master node this force will be applied to the master node and then the nodes which are linked or tied to the master node will have this the same load transform. Okay, uh, equivalent load applied to the contour of the of the tied nodes. Okay, we see here we have different tying connections. We have defined connections here for the loading, and we have defined as well connections here to define to simulate bolts. Okay, and here to simulate a welding spot, because we know our worst part of the structure will be here. We simulated a welding spot with a stiff defining springs with stiffness. Okay.
Okay, so now after the modeling process has finished, we wanted to perform the nonlinear analysis of steel to see how much we could go past the critical load for the client. So we perform an nonlinear analysis using 10 times the critical load. We could see the actual magnitude of the critical load. So now we can we can load the results. Okay, we want to show the results on this plate. That's the critical one where the welding is done. So we can use the new feature of CivilFEM where we can click the plate we want to show results on and create a quick selection group. Here you can see that we have created a selection called current selection, and now we can load the results and plot the results only on that element. So we can plot on the selection. Okay, first we want to see the, for example, the wall displacement in millimeters, and we click OK.
We have defined the contacts between between this plate and the T plate.
So this is the Y displacement of the first step, and we can go to the last step to see the total displacement in this critical point. So as you can see, the Y displacement is 1 millimeter, 0.38.
We can check as well the stresses.
And we can see the stresses, of course. For example, the von Mises stress is very significant. Okay, we plot it. Okay, as you can see, the yielding of steel has been reached. We have above 275. This is an S275 steel. So all the red parts of the model are yield.
Yeah, we can plot the plastic strain.
Okay, the equivalent plastic strain tells us where which parts of the model has yielded. Okay, of course this is the critical part where we have okay, we have use average, so we can see the maximum
stress will be there.
Stress. Okay, and that's the model of the plate. We can show you one more thing.
The full model.
And the full model, okay. So we can go to the structural elements, select all and show them. So you can see the default shape of the final model, and we are going to show for example, the Z displacement. So you can see the actual maximum displacement of the plate. The form shape, okay. So you can see the maximum displacement occurs at the
tip of
the plate. Okay, now we can show another advanced feature of CivilFEM. We talked in the PowerPoint about the Python scripting. We have prepared a short script where a very useful one, because we can show the actual loading process that in a linear case such as this one, how it takes place. So we load the script editor and we can load the script, and here we have a Python script. I'm going to go to play it, and this script is going to perform a loading of all the result files. So there are 64 files, so we need to load them, and we are going to create some vectors. With these vectors, we are going to plot three figures as they have appeared here. We can show the von Mises stress on each of the loading steps. This means that the first load step is zero load, and here we have the yielding the yielding of steel can be seen here in the von Mises stress. So from the beginning of this step is 2022. We know that the steel is going to yield. The same goes for the Z displacement. As you can see here, we have a linear branch, and then when we reach the nonlinear branch of steel, the displacement increases exponentially. And this shows us the equivalent plastic stress. So here we don't have any yielding of the material, and here we go into yield. So we can have several conclusions on this. We have that the 22% of the critical load we have applied, the material starts yielding, and it breaks at the 63 step. So this is the analysis of the plate.
Yes, of course. Well, you can see here all the capabilities of using a Python script. Okay. Well, another or last example, the last but not the least. Okay, is just a very simple model, a beam model, as you can see here. Well, I can show you. There are two lines, and I want these two beams to get in contact. Okay, I have defined just steel material. As you can see, well, the units were the international system units by default, but anytime I can change the viewing of any units in any system. Okay, I can mix them or anything over the same. For the section, I have defined an IP 120 section. Okay, I can see here the different dimensions in different magnitudes. Okay, I have here millimeters, but I can set the display in another unit. Okay, I can change, if I change the dimensions. Okay, it will be updated automatically. Okay, I will leave them as the one before. As we told you before, now we have the new capability of selecting nodes. Okay, if we select a node, we can apply on it any entity, any load or any nodal constraint. Okay, in this case, I want to apply a load in just at the tip of this cantilever beam. Okay, will be applied here, and I want to apply a boundary condition on these nodes here. This beam will be clamped well, no, cantilever, only one end fixed, and this other one will be constraint. Okay, I will fix the all degrees of freedom. Okay, I have defined it here, and I have it here. Okay, this is our boundary condition, and well, as you can see, this beam is has an orientation. Okay, I have defined well, it's not completely straight. I had set an orientation. I can change it here. Well, I will leave, but I leave here 20 degrees. Okay, so the result is just in a static case we apply just a load, and this beam will be in contact with this other one. Okay, to do that we had to find a contact pair, just to set which is the beam to be contacted, the one at the bottom, and which will be the contacting beam, which is the one at the top. Okay, well, the force is applied, and then after solving I will have results. As it's nonlinear analysis, our dot case will be divided into different increments. Okay, our one of the typical results to check the status of this contact. If I clear the loads, if I check here, I will put you so we can see it better. I can check the contact status. I will set the scale to 1 and the formed shape. Okay, as you can see, now at this step the beams are in contact, and I can check any kind of result, as any stresses. Okay, as you can see, they are actually just as I told you, just beams. They are just lines, but here you can see how they contact using the real shape. They will contact from the bottom flange to this top flange of the one of the bottom. As you can see, how the beam at the bottom will start to bend until, well, at the final step will buckle. Okay, as you can see here, and it's very common as well. Well, very useful to see another result, which will be, for example, the bending moment. How will when any result? Okay, we will see the bending moment. We will set 2D view, which will be maybe better to locate how the first at the beginning the moment is almost practically zero, but once the beams are getting in contact, as you can see, once the beams are getting in contact, the bending moment of the diagram of the beam at the bottom will start getting the shape of the typical bending moment diagram of a clamped beam, which has the two ends fixed. Okay, as you can see here, the 2D view and the 3D view. Okay, well, from this point we can decide, well, how to check, for example, these elements, these elements of here. We want to perform a code checking. Okay, a new selection, and we can select here any code. For example, we can choose the Indian standard, the one of the latest codes which were implemented, and then perform a bending buckling, because we know that those elements are well, will be into a bending moment or big buckling forces. Okay, once we perform the checking, we can select this and plot the total, well, the total criterion of this is the total structure. But if we want to do only for the current selection, will be these ones. Okay. So, well, this simple example just show you all these powerful nonlinear capabilities of CivilFEM powered by Mark.
Okay, so this is all for today. This is information and contact. We can reach us in civilfem.com, or here are the emails of our executive staff. So if you want, you have any question, you want to contact us regarding CivilFEM or any doubt you have about
Yes.
Cyber or software.
Yes, if you're interested in any feature that, of course, we will have a next following webinar. So if you're interested in a certain or particular tool, just
contact us and using the usual channels. So thank you for your attention, and see you on the next one. Thank you very much.
bye. Thank you.